Assalamualaikum warahmatullahi wabarakatuh and a very good morning everyone. So today we continue our lesson on digital electronics chapter 8, counters and shift registers. So this is the second part of this chapter that you will learn, which is about shift registers. So at the end of today's lesson, you are expected to know what is shift registers and how to operate the shift registers and how to design the shift registers in digital electronic circuit. Okay, so without further ado, let's begin. Okay, first I will tell about the introduction of shift registers. So what is actually shift registers? So shift registers consist of arrangement of flip-flops in which it is used to store data and also shift data. So basically, a shift register consists of an arrangement of several flip-flops. So it uses the application of flip-flops to shift data inside digital circuit. Okay? So basically, shift register, it is used to store data and also to shift data. So we can have two functions of shift registers. So the storage capability of a register makes it important type of memory device. So for example, this is the concept of storing a data 1 for D flip-flop. So as you have learned in the previous chapter, so for D flip-flop, if this is actually the positive edge triggered, so at the rising edge, the output of the D flip-flop will follow the input. So in this situation, the input is 1, so the output will become 1 at the rising edge. So this is the concept of storing a data of 0 for D flip-flop. So to store the data 0 in D flip-flop, what you need to do is you need to give the input of 0 to the D flip-flop. And then at the rising edge, the output will become 0. Okay, so this is actually how what you call a simple concept of storage capability of a register. Okay, so next we'll go through for some types of shift registers. So there are several types of shift registers. So we have serial in parallel out, SIPO. We have parallel in serial out, PISO. We have parallel in parallel out, PIPO. And we have serial in serial out, SISO. So today we will go through all these types of shift registers so that you will be able to understand and you will be able to learn about the types of shift registers. Okay, the first part that you will learn is SISO, which is serial in and serial out. So what is actually a serial in and serial out shift registers? So the SISO accept data serially, 1 bit at a time on a single line. So in digital electronics, serial means you must have only 1 bit data flow at one time and you only have a single line of data. You cannot have a multiple line. Okay, for example, so the data in will be flow throughout this is the representation of the shift registers and this is the data out. So it will be travel in one line only, a single line. Okay, and it will transfer only 1 bit at a time. So this is serial in, serial out. Okay, at every clock pulse, 1 bit of data in will be entered the shift registers and at the same time, 1 bit will be shifted to data out. So from this statement, you are able to understand how the SISO works, where in each clock pulse, only 1 bit of data will be entered the shift registers and at the same time, only 1 bit of data will be shifted out to data out. Okay, so in each clock pulse, 1 data will be inserted into shift registers and 1 data of input will be shifted out from the shift register. Okay, so this is the example of a 4-bit serial in serial out implemented using D flip-flops. So you see here, this is the circuit of the 4-bit serial in serial out. So from here you can see that the clock input is connected to each flip-flop. Okay, so that in each clock the changes will be taken at each flip-flop. So each flip-flop will change at every clock cycle. Okay, So this is the input of serial data. So the serial data will queue up here, okay, in one single line. Okay, at each clock, each serial data will be moved throughout the shift registers. Okay, so it will move throughout the what do you call flip-flop 0 to flip-flop 1, and then to flip-flop 2, and then to flip-flop 3, and then we can observe the output from the flip-flop 3. So in this type of shift registers, it only have two input, which is serial data input and also CLK, which is the input clock, and it has two outputs, which are serial data output and serial data output bar. Okay, so this is the logic symbol of 4-bit CISO. Okay, they have two inputs, data in and clock, and also they have one output. So you can either choose the Q3 or Q3 bar as your data out. Okay, so SRG, what we call represent the shift registers. 4 is 4 bits. Okay, so now I will show you example on how what I call serial in serial out works. Okay, so shows the state of 5-bit register in figure below for the specified data input and waveforms. So assume the register is initially clear. So from this example, what information that you can get is you must assume the register is initially clear, and the type of shift register is 5 bits. Okay, so this is the the circuit of the 5-bit register. So if what you need to know is, if you have a total of 5 bits, you need to have a total of 5 D flip-flop. 1, 2, 3, 4, and 5. Okay, so the example wants you to show the state of 5-bit register in figure below for the specified data input and waveforms. Okay, so this is the clock signal that has been given. They have 1, 2, 3, 4, 5 clock signals, and the data input that they wanted you to transfer is 1, 1, 0, 1, 0. So you need to transfer the data of 1, 1, 0, 1, 0 to inside the shift registers. So how does it work? So let's take a look at the next slide. So in the previous question, you have been given an input of 1, 1, 0, 1, 0, and then the shift register is initially set to 0, 0, 0, 0, 0, because in the previous example, it shows you the initial output is equals to 0. Okay, so all the output is initially 0. Okay, so right now we have the input of 1, 1, 0, 1, 0. So the MSB will enter first because we wanted to observe MSB first, right? Okay, so MSB part of the number will enter first. Okay, so at the first clock cycle, the flip-flop will change its output. Okay, so for example, for this, we start from the flip-flop 4. So the data that comes from flip-flop 3 will be transferred to flip-flop 4, and it will flow throughout the other register. Okay, so all at each clock cycle, so for the first clock cycle, the data will be transferred from each flip-flop to the next flip-flop. Okay, so after the data is being transferred, so right now you already transferred the input of 1, and then the remaining input is 1, 0, 1, 0. So right now you have 1, 0, 1, 0. So at the second clock cycle, the same operation continues, where the output of FF3 will be transferred to FF4, FF2 will be transferred to FF3, FF1 will transfer to FF2, and FF0 will be transferred to FF1. Okay, so you see here, it will be transferred. Okay, it is transferring. So right now it will become 0, 1, 0 because the first and the second data input has been transferred. So the remaining is 0, 1, 0. So you can get the output from the flip-flop 1, 1, 0, 0, 0, 1, 1, 0, 0, 0. Okay, so at the third clock cycle, the same procedure is happening. Okay, where 0 is transferred to 0. Okay, 0 transfer to here, 1 transfer to here, 1 transfer to here, and 0 transfer to the output of flip-flop 1, and it will become 1 because 1 1 0 has been transferred inside the clock cycle number 3. And at the next clock cycles, so it will be transferred 1 0 1 is here, 0 will be transferred to here, and 1 will be transferred to here. Okay, so you can just draw the waveform based on the shifting operation which has been done in seesaw shift registers. So at each clock cycle, one data will be transferred from the flip-flop. Okay, so at the 5th clock cycle, you see here. Okay, so right now all data has been transferred. You see here, they wanted to transfer the data of 11010, and then all the data has been inserted inside the flip-flop. So this is the output that comes from flip-flop. So the output inside the flip-flop is 11010. So it means that the input data right now at the 5th clock cycle, it has been transferred in all the output of flip-flop. Okay, so after that, in the next clock cycle, the input of 0, okay, the general input of 0 will be entered and will be inserted inside the flip-flop for the next clock operation. Okay, so in order for you to get better understanding, let us see the operation table for the seesaw shift register, which is the 5 bits based on the example that have been given. Okay, so the input that has been given to be transferred is 11010. Okay, so 11010 will be inserted into the flip-flop. This is flip-flop 0 1 2 3 4 5 is 0 1 2 3 4, and all of this will be combined to become the seesaw shift registers. Okay, so at the first clock cycle, so the data of 1, the MSB data will be inserted into the flip-flop. Okay, because the initial data of all flip-flop are 0. And then at the first clock cycle, the MSB data, which is 1, okay, will be inserted into the flip-flop 0. And then it will remains the input of 0101, okay, because 1 has been transferred here. So on the next clock cycle, okay, this data, which is the data of 1, will be inserted into flip-flop 0, and the output from flip-flop 0 will be shifted to flip-flop 1. Okay, so at the 3rd clock cycle, so you have been transferred the input of 1 inside the flip-flop 0 on the 2nd clock cycle. So on the 3rd clock cycle, you will be transferred the input of 0 on flip-flop 0. Okay, so 0 will be transferred to flip-flop 0, and from flip-flop 0, the output data from flip-flop 0 will be transferred to flip-flop 1. The output data of flip-flop 1 will be transferred to flip-flop 2. And then the cycle continues until all of the data has been transferred. So at the 5th clock cycle, you see here, the data bit are stored, okay, inside the flip-flop. We want to transfer input of 11010, so we have the input of 11010 inside the flip-flop. So right now, as you can see from the previous slide, the seesaw shift registers only have one output. Okay, so one output can only be observed at one time. So it means that one output will be changed only at each clock cycle. So at 6th clock cycle, so 0 will be automatically inserted into flip-flop 0 because we wanted to shift the input of 0101 will be shifted out, so it will become 0101. Okay, and then 0 will be inserted in the next clock cycle, and more 0 will be inserted because we wanted to push out the output. Okay, so the output read 1 bit at a time until 9 cycles. So right now we wanted to transfer the input of 11010. Okay, so for seesaw we only have one output, so all of the output will only be observable at the clock cycle 9, because at clock cycle 5, the output of the shift register, which is equals to the output of flip-flop 4, will be equals to 1. Okay, 1. And then at the 6th clock, the output of flip-flop 4, which is the output of the shift register, will become 1. So it has been transferred the second data, 1, and then 0, the third data on clock 7. And at clock 8, it transferred the next data, 1. And at the 9th clock cycle, it transferred the data 0. So at from the clock of 5 until clock of 9, we can observe the transferred data that we are initially wanted to transfer at the beginning of the clock cycle. Okay, and at the 10th clock cycle, so the data bit shifted out after another 5 cycles. So after another 5 cycles, the transferring data is done. Okay, so note, therefore, for n-bit CISO, okay, it requires n clock cycle to shift in all the data set. Okay, so this is the example of 5 bits CISO. So for 5 bit CISO, at the 5th clock, all of the input data has been transferred and has been saved inside the shift registers, because 11010 has been transferred. Okay, the input has been transferred, but it requires another n clock cycle to shift out all the data set. So we need 5 more clock cycle in order for us to observe all of the input that we wanted to transfer. So it requires 5 more clocks. So until clock 10, we can observe all the all the data that we wanted to transfer. Okay, at 5th clock cycle, we can see our first data that we wanted to transfer. At the 6th clock cycle, the second data will be present. At the 7th clock cycle, the third data will be present. At the 8th clock cycle, the 4th data will be present, and at the 9th clock cycle, the 5th data will be present. Okay, so after the 10th clock cycle, all the data has been shifted out from the shift register. So it has been completed after 10 cycle. Okay, this is the example of 5 bit of shift registered serial in, serial out. Okay, so next is serial in, parallel out. So how does this shift registers works? Okay, so previously we have learned about CISO, which is serial in, serial out. So right now we are learning about serial in, parallel out. So the serial in, parallel out, the data bits entered serially at a time, but the output is parallel. So all bits are available simultaneously, but only after n clock cycle for n bit SIPO. So for serial in, parallel out, we can observe the output of the data that we want to transfer after n bit of clock cycle. For example, if we wanted to transfer 5 bit of data, we are using 5 bit of shift registers. And we can observe the output after 5 clock cycle. So this type of shift registers requires a lower number of clock cycle in order for us to observe all of the output that we wanted to transfer. Okay, because previously CISO requires 5 clock cycle to store, and then another 5 clock cycle to display the data at the output. But for SIPO, if we have 5 bits of data, it requires only 5 clock cycle in order for us to transfer the data. So we can see the output after 5 clock cycle. Okay, so the data in will be inserted serially, but the data out will be displayed in parallel. Okay, so for CISO, output only at Q3, but the output for SIPO is at Q3, Q2, Q1, and Q0. So from this statement, it means that for CISO, we only have 2 inputs, which is the data in and also the clock cycle. Okay, but for the for the SIPO, serial in, parallel out, we have a total of 2 inputs as usual. Okay, data in and also the clock cycle, and we have a total of 4 outputs: Q3, Q2, Q1, and Q0, which will be simultaneously transferred at each clock cycle. Okay, so this is the example of 4-bit SIPO implemented by using the flip-flop. So you see here from the logic symbol, you can observe that it has a total of 2 inputs, okay, data in and also clock signals, and it has 4 bits of output. For example, for this one example, I'm using the 4-bit shift registers, so it has 4 bits of output. If 5 bits of shift registers, it have 5 bits of output. So you can observe each output at the same time. So the circuit is just similar to the seesaw, but only you are having an extra output here. Okay, just get the the circuit here, the wire here, and then you will get Q0, and the same things happen to Q1, Q2, and Q3. Okay. So the timing shown, the waveform diagram when 0, 1, 1, 0 is shifted through the register. So assume the register is initially set. Okay, this example show you how you can observe the operation of SIPO. Okay, so right now we wanted to transfer the data of 0, 1, 1, 0. So assume the register is initially set. Okay, so this time we are considering the set situation. So Q0, Q1, Q2, and Q3 will become 1. Okay. So right now we wanted to transfer the data of 0, 1, 1, 0. So the MSB will enter first. Okay. So 0 will be transferred in the first clock cycle. Okay. 0 will be transferred to the flip-flop 0. Okay, so it will become 0 and the other will become 1 because the initial state is 1, 1, 1, 1. So 0 will be shifted to the flip-flop 0. And then we have remaining of 0, 1, 1. So this is the data that will be transferred after this. So at the second clock cycle, the data 1 will be transferred to the flip-flop 0. And flip-flop 1 will have the output from the previous flip-flop 0. So 0 from flip-flop 0 will be transferred to the flip-flop 1. And then we have the remaining data of 0, 1. So 0, 1, 1 will be transferred to flip-flop 0. And the remaining will be transferred from the previous flip-flop. Okay, so right now we have only the the data of 0. So 0 will be transferred to flip-flop 0, and the previous data of each flip-flop will be transferred to the next flip-flop. So right now we can see that all the data has been transferred into each flip-flop because we wanted to transfer 0, 1, 1, 0. Okay, so inside each flip-flop we already get 0, 1, 1, 0. So because the SIPO has a total of 4 outputs that can be observed, so right now output start and read simultaneously after 4 cycles. So after 4 cycles, you can already observe what are the output that you wanted to transfer inside the shift registers. So from this statement, what you can say is that the SIPO has a lower clock cycle that required, which in order for you to observe the output of the transferred data. Alright, so it is easier for you to observe the output of transferred data by using SIPO, okay, compared to seesaw. Okay, next we go through the SIPO IC. So for SIPO IC, we have an IC of 74X164. So how does the SIPO IC works? So the 74X164 is an IC shift register having a SIPO operation. Of course, because we are studying the SIPO IC, so it will be having a SIPO operation. So the device has 2 gate serial input A and B and a clear input CLR bar. So the parallel output are Q0 to Q7. So from these points, what you can say is that the SIPO IC is actually the 8-bit SIPO shift registers. Okay, so shift register 8-bit. So this is the logic symbol of 74X164 SIPO IC. So it has 2 serial input, okay, which is A is being used to transfer the 8 bits of data, and B, it is actually used as an operation enable. Okay, so CLR bar, it is used to clear the the shift registers, and clock, it is used to shift the data, okay, at each positive age triggered clock cycle, because we doesn't have any bubble here, so it is positive age triggered shift registers. Okay, so this is the parallel output, so it has a total of 8 parallel output, so it is 8-bit shift registers. So can you guess how many flip-flops are inside these shift registers? So because it is an 8-bit shift register, so it will have a total of 8 flip-flops. Okay, so this is the sample timing diagram for 74X164. Okay, so notice that the serial input data on A, okay, so this is the input that we wanted to transfer. So the serial input data on A only shifted into and through the register after input B goes high. Okay, so right now we wanted to transfer the serial input A inside the shift register. Okay, so serial input A will be transferred, but it will only be transferred after the input B is becoming 1. Okay, after input B is become 1, the data inside the serial input A will be transferred. Okay, so as you can see from this timing diagram, the output is initially reset. So initially, all of the output of each shift, in each flip-flop will become 0. Okay, all will become 0. And after the serial input B is become 1, that comes after this red line, so data will start shifting. Okay, so right now this is time where the serial input B is equals to 1. So at the positive age triggered, you can see here the serial input is equals to 1. So therefore Q0 will start shifting first. Okay, so the Q0 will become 1. Okay, so at each positive age triggered, the data from serial input A will be transferred. So right now we wanted to transfer 11010000, which is 8 bits of data. Okay, so the data will be shifted at each clock cycle. And can you guess at what clock cycle the data can be observed? So at 8 clock cycle, because it is 8 bits of SIPO shift registers. So we have 1, 2, 3, 4, 5, 6, 7. So this is at 8 clock cycles. So we can observe the input that we wanted to transfer, because we wanted to transfer 11010000. So 11010000. So at 8th clock cycle, you can observe the data that you wanted to transfer. Okay, so the output represented after 8 clock cycle for 8 bits of output. So in this timing diagram, after 8 bit of output, so an input of 0 is given to the CLR bar. So it means that we want to reset the output. So after this point, so the output will be reset. So the output will become 0. Alright. So this is how SIPO works. Okay. So the SIPO IC is actually 8-bit SIPO shift registers. So after 8 clock cycle, you can observe what is the input that you wanted to transfer inside the shift registers. Okay. So at each clock cycle, the input will be shifting out. Okay. Okay, next is piezo. So can you guess what is actually the annotation of piezo? So actually piezo is actually parallel in, serial out. So the piezo, data bits entered simultaneously into respective stage on parallel line, while outputs are 1 bit at a time. So it is actually same in CISO, because we have only one output, but we have multiple input. So the only different piezo compared to the CISO, okay, is only at the input number. Okay, so the data in is in parallel, but the data out is in serial. Okay, parallel in, serial out. So for piezo, there are one extra input, which is shift or load bar input. So what is the function of shift or load bar? So I will explain to you what is the function of this input later on in this slide. Okay, so 0 if the input of shift or load bar is equals to 0, it means that the shift registers will load the input values. And if the input of shift or load bar is equals to 1, it will shift them out at clock cycles. Okay, so they have two different type of mode, okay, for shift registers. Either they want it to load or they want it to shift. Okay, so this is the logic diagram of 4 bits piezo using D flip-flops. So for piezo, we have extra logic gate here. So extra logic gate here, it is used to enable the function of shift load. Okay, so all of this logic gate, it is used to design the different mode of piezo. Either they want it to load the data or they want it to shift the data. Okay, so for the piezo, we have a total of 4 input of data in, 1 input of shift or load bar, and also 1 input of clock cycle. So we have a total of 6 different input, and we only have 1 output only. So this is represented in the logic symbol of 4 bits piezo. So this is the equation for the input of each flip-flop inside the piezo shift registers. So as you can see here, the first equation given is for the flip-flop 0. So the input of flip-flop 0 only allows the input to be loaded. Okay, so therefore the equation is just only equals to D0, because it can only allow the D0 to be loaded if the input of shift load bar is equals to 0. Okay, so next is the equation for D flip-flop 1 input. Okay, so it is equals to Q multiplied by shift plus load bar multiplied by D1. So you can see here that it has a total of 4 different variables. We have Q0, shift, load bar, and also D1. So the input of Q0 is actually comes from the previous flip-flop. Okay, so the Q0 is actually the output of previous flip-flop, which will be given to flip-flop 1. And the D1 is actually the external input, which is given to the data in pins inside the 4 bits piezo. Okay, so in order for you to define the value of shift and load bar, what you need to do is you need to observe at the current status of shift load bar input. So if shift load bar input is equals to 0, it means that the load bar is equals to 1. And the shift will be equals to 0 because it is in load mode. And if the input of shift load bar is equals to 1, so the shift variable will become 1 and the load bar variable will become 0. Okay, so from this statement, what you can say is that if the input of shift load bar is equals to 0, so it means that it need to load the what they call the data. So for example, on flip-flop 1, in order to load the data, the shift load bar must be equals to 0. So the what they call the input which will be observed at D of flip-flop 1 will be equals to D1. But if the mode is in shift mode, the input that you can observe from flip-flop 1 is Q0, because we want it to shift the data from Q0 to the second flip-flop, okay, to flip-flop 1. Okay, so this statement is applied to other types of flip-flop, flip-flop 1, flip-flop 2, and flip-flop 3. Okay, so it is similar. Alright, so next, what is actually load mode? So the input must be available at parallel input D3, D2, D1, and D0. So in order for you to load the data, you must ensure that all inputs must be available at the input pins. Okay, so when shift load bar is equals to 0, so it means that it is in load mode. The data loaded to the 4 flip-flop inside the shift register at the positive edge of the clock. Okay, so the data will be loaded after the positive edge has been detected, because it is positive edge trigger shift registers. So the MSB of the data will appear at data out. Okay, so the first data that you can observe when you are in load mode is the MSB data. Okay, so next is the shift mode. So when shift load input is equals to 1, So the data will be shifted on every positive edge of clock cycle. So right now, if it is in shift mode, the data will be shifted so that we can observe all the data that we wanted to transfer. Okay, so after the 4 clock cycle, the LSB data will appear at data out. So it means that after 4 clock cycle, you can observe all of the data that you want to transfer. So at the 5th clock cycle, all the 4-bit data set will be lost and replaced by a new set of 4-bit data. Okay, so after we are having the 5th clock cycle, so all of the data transferred has been completed. So it will be replaced by a new set of 4-bit data. Alright. So this is the example that I will show you for piezo shift registers. So show the data output waveform for a 4-bit register with the parallel input data and shift load bar waveform as follows. So from this example, we are given piezo shift registers with a total of 4 bits because it has 4 bits of input load. I will call input data. Okay, so this is the shift load input and also the input clock. So this is the active high. Okay, so it has only one output, which is serial data out. Okay, for piezo shift registers, what you need to observe first is you need to observe the current condition of shift load bar in order for you to define what are the output that comes from each flip-flop inside the shift registers. Okay, so in this example, this is the truth table that we obtained by using 4 bits of piezo shift registers. So as you can see here, at the first clock cycle, the input of shift load bar is equals to 0. So it means that the shift registers is currently inside the load mode, where it will load all of available data which is being connected to the data input pin. Okay, so right now we wanted to transfer the data of 0, 1, 0, 1, where 0 is the MSB and 1 is the LSB. Okay, so at the first clock cycle, when it is in load mode, what you can observe is that you can observe the data of MSB, okay, at the serial data out. So the serial data out is actually equals to the output that comes from flip-flop 3. So you can observe the value of 0, which is equals to the MSB of the data that you wanted to shifting. Okay, so at the next clock cycle, you see here it is equals to 1. So the input of shift load bar is equals to 1. So it means that the data shifting mode is taken care, what I call is conducted. Okay, so the data bit shifted out after another 5 cycles. Okay, so after the first clock cycle, so each data that comes from flip-flop 0, flip-flop 1, flip-flop 2 will be transferred to the next flip-flop, where the data from flip-flop 0 will be transferred to flip-flop 1, flip-flop 1 will be transferred to flip-flop 2, and flip-flop 2 will transfer to the flip-flop 3, and so on at each clock cycle. Okay, so as you can see here, the output read 1 bit at a time until 4 cycles. So at this type of shift registers, because it is a serial output, so we can only read 1 bit at a time, okay, because it is serial. Okay, and after 4 cycles, we are able to read all of the input that we wanted to transfer. Okay, so as you can see in this truth table, so you see here the X indicates the don't care condition, where it doesn't care, either it is 0 or it is 1. Okay, so what we wanted to observe here is that we just wanted to observe the data that we want to transfer inside these shift registers. Okay, so the last data that we can observe inside this shift register is the LSB data, which is equals to 1. Okay, alright, so this is the solution for the example. So the example asks you to show each output that comes from the flip-flop inside piezo shift registers. Okay, so first thing that you need to do is, as I've been mentioned before, so first you need to observe the current situation of shift load bar. So the first condition is shift load bar is what I call the input of shift load bar is equals to 0. So it means that it is in load mode. So it will load anything that is available at the input data D0 until D3. Okay, so right now the data D0 until D3 is 0, 1, 0, 1. So it will automatically loaded the data of 0101 at the output of the what they call each D flip-flop, because in D flip-flop the output will be equals to the input at each positive age triggered clock cycle for positive age triggered flip-flop. Okay, so at the next clock cycle, what you can say is that each data from flip-flop 0 to flip-flop 2 will be transferred to the next flip-flop, where the output data from flip-flop 0 will be transferred to the data, what you call, will be transferred to flip-flop 1. So the output that comes from flip-flop 1 will be transferred to flip-flop 2, and the output from flip-flop 2 will be transferred to flip-flop 3. So at the fourth clock cycle, you can observe all of the data that you wanted to transfer, okay, where you are getting the same input data which has been connected to the D0 until D3, 0101, and after four clock cycle, you can observe the output of 0101. Okay, so this is a piezo shift registers where you have the parallel input and you have the serial output. So you can transfer 4 bits at a time, but you can only observe 1 bit at a time. Okay, so next is PIPO. What is actually PIPO shift registers? So the PIPO, input and output, are done in parallel. So PIPO is actually parallel input and parallel output shift registers. So when enter the inputs, bits appear on the parallel outputs. So for these shift registers, we are having the parallel input and also parallel output. So this is the logic diagram of 4-bit PIPO using D flip-flop. So for PIPO, any things that you any data that you are connected, any data that you are given, that you wanted to give to the PIPO shift registers, will be automatically appear on the output. After, for this one, we have positive age trigger, right? So after 1 clock of positive age trigger signals, you already can observe what are the data that you wanted to transfer. Okay, for example, you want to transfer data of 0101. So after the first clock cycle, you already can observe the output of 0101 for PIPO shift registers, because both inputs and outputs are parallel, where you can transfer 4 bits of data and you can observe 4 bits of data at the same time. Okay, so next we go through the universal bidirectional IC, which is 74X194. So what is actually the universal bidirectional IC? So how does it works? So the 74X194 IC is a universal bidirectional shift registers, okay, as I've been mentioned inside this title. Okay, so it has both parallel and serial input-output capability. Okay, so before we proceed, I wanted to show you what are the pin configuration of this IC. So this is the logic symbol of 74X194 universal bidirectional IC. So you see here it has a total of 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 different pins, where D0 until D3 are the parallel inputs. Okay, CLR is actually a clear, okay, where you wanted to clear your shift registers. S0 and S1 is operation mode, where the shift registers can operate in different types of modes. Okay, so later on I will show you what are the available modes inside this 74194 shift registers. And SR, SER, and SL, SER is the serial input output. Okay, where it is shift right or shift left. Okay, so this is the input clock as usual. So if you want your IC 74X194 to work as different types of shift registers, so you must know where you wanted to put your input and where you wanted to put your output. Okay, first, you wanted to design a SISO, serial input, serial output shift registers by using this IC. What you need to do is you need to connect your input to either SR-SER or SL-SER. And you can observe your output of serial at the Q3. Okay, so for this type of shift registers for SISO, if you want your output to be shifting to the right, you must connect your input to SR SER, which is shift right SER, serial. Okay, if you wanted to shift left your output, you must make your input to be connected to the SL SER. Okay, and then you can observe your output at Q3. Okay, Q3 pins. Okay, so if you wanted to operate as SIPO, serial in parallel out, you must either connect your serial input at the pin of SR/SER or the pin of SL/SER, and then you can observe your output at Q0, Q1, Q2, and Q3 directly. Okay, and if you wanted your shift registers to operate as PISO, parallel in, serial out, so you must connect your parallel input to D0, D1, D2, and D3, and you can observe your serial output at either SR/SER or SL/SER. And finally, if you wanted your shift registers to be operated as PIPO, parallel in, parallel out, so you must connect your input to D0, D1, D2, and D3, and then you can observe your parallel output at Q0, Q1, Q2, and Q3. Okay, so you must know where you want to connect the input and output if you want your shift registers to be operated as SISO, SIPO, PISO, or PIPO. Okay, so next I will show you different modes that are available in 74X194 Universal Bidirectional IC. Okay, so the first mode that is available is the hold mode. Okay, the hold functions. So in order for you to activate the hold function, so you must give an input of 0 to S1 and 0 to S0. So what does it mean by hold mode? So in hold mode, it will what we call hold what is the current value at the output. Okay, so whatever current value of outputs, it will retain, so it will not change if the shift registers is in hold mode. Okay, so next is the shift right. Okay, the shift right mode. So what is actually shift right mode? So in order for you to activate shift right mode, you need to get what you need to give the input of 0 to S1 and input of 1 to S0. Okay, and then it will activate the shift right function. Okay, for shift right function, this is the next value of Q0, next value of Q1, next value of Q2, and next value of Q3. So for the next value of Q0, a new input will be inserted in order for us to shift the output to the right. Okay, so the next output of Q1 comes from the previous output of Q0, when the next output of Q2 comes from the previous output of Q1, and the next value of Q3 comes from the next the previous output of Q2. Okay, so this is shift right mode. Okay, for shift left mode, if you wanted to activate the shift left mode, what you need to do is you need to give the input of 1 to S1 and you need to give the input of 0 to S0. Okay, and the next output of Q0 comes from the previous output of Q1. The next output of Q1 comes from the previous output of Q2. And the next output of Q2 comes from the previous output of Q3. And the next output of Q3 comes from the new input. Okay, so new input will be inserted. Okay, so for shift left, the new inputs will come from SL/SER, and for shift right mode, the new input will comes from SR/SER. Okay, so next is the parallel load. So what is actually parallel load? So in order for you to activate this function, what you need to give is you need to give the input of 1 to S1 and you need to give the input 1 to S0, and then the output that you can get in this mode, in this parallel mode, is directly from the parallel inputs. Okay, so if it is actually the loading functions in shift registers where you wanted to load the inputs of D0, D1, and D2 and D3 inside your shift registers. Okay, So you can directly see the input of D0, D1, D2, and D3 at the output Q0, Q1, Q2, and Q3 inside the parallel load mode. Okay. So next, I will show you the timing diagram for 74X194 shift registers. So right now you can see how does it actually work. Okay. So for this timing diagram, as usual, it consists of the input clock. Okay. And then it has mode control inputs. So previous slide, I already shown you different modes of the universal bidirectional IC. And then you have the clear input, and then you have serial data input. So either you want it to use SR or SL. So it is depending on the mode. Okay. Next is the parallel data inputs and also the parallel outputs. Okay. So the first what do you call the sequence of the clock. Okay. So you can see here at the first operation sequence. So right now you can see the clear mode is activated. Okay, you can see the input of 0 is being exerted at the clear clear bar. Okay, so it means that the output will become 0 because the shift register is being cleared. All right. So at the next sequence, okay, at the next rising edge, you see here that the mode control inputs is equals to the S1 is equals to 1 and S0 is also equals to 1. So it means that the load mode is activated. Okay. So when the load mode is activated, it will store whatever value that are available at parallel data inputs. Okay. So right now, the parallel data input at the rising edge is equals to 1010. So it will be automatically transferred to each flip-flop output inside the shift registers. So the parallel output of Q0, Q1, Q2, and Q3 will be automatically become 1010, which is similar with the parallel data inputs because it is in loading mode. Okay, because S0 and S1 both are equals to 1. Okay, so at the next clock cycle, the next rising edge of clock, okay, you can see that the mode control inputs are constantly. Okay, it is constant. So it is S0 equals to 1 and S1 equals to 0. So it means that the shift right mode is activated. Okay. So for this mode, what you need to do is you need to observe the input at SR SER because it is in shift right mode. Okay. As it is in shift right mode, you need to only observe the SR SER input. Okay. And then the SR SER input will be automatically transferred to the Q0 at each rising edge. Okay, so at each rising edge, each value of the from SR SER will be transferred to the Q0. Okay. All right. So at each clock cycle at this mode, okay, at each clock cycle in shift right mode, the output of each flip-flop will be transferred. Okay, so previously I already shown you the the operation of shift right, shift left, load, and also hold. So for shift right, you must know what is the next output of each flip-flop. Okay, so for shift right mode, for example, the next output of Q1 will comes from the previous output of Q0. And the next output of Q2 will comes from the output of Q1. Okay? And the next output of Q3 will comes from the previous output of Q2. So those sequence are repeated in each rising edge clock cycle until you see the changes on the mode control inputs. Okay, so this sequence are repeated until it reach at this state where the mode control inputs are changing. Okay, so at this this marked, okay, at this box, so the mode control inputs has been changed to S0 equals to 0 and S1 equals to 1. So at this time it is in shift left mode. So for shift left mode, the input that you need to observe is at SLSER. Okay, so right now at SLSER, at each rising edge, the input is given as 0, 1, 0, 1, 1. Okay, for shift left, each input from SLSER will be automatically transferred to Q3 at each rising edge. Okay, so at the first rising edge, 0 will be transferred. At the second rising edge, 1 will be transferred, and so on. Okay, so at each clock cycles, each output from the flip-flop will also be shifted to the left. Okay, so you must know what is the sequence of the output. Okay, how we wanted to get the current output from each flip-flop. Okay, from this in this mode, okay, in shift left mode, for example, the next output of Q0 comes from Q1. The next output of Q1 comes from the previous output of Q2. And the next output of Q2 comes from the previous output of Q3. So this sequence is actually inverse compared to shift right. Okay, so what you need to know is that you need to know the correct sequence of the current output of flip-flop. Okay, for shift right, the current output of Q1 comes from the previous output of Q0. For shift left, the current output of Q1 comes from the previous output of Q2. Okay, so you must know the correct sequence in order for you to answer the question correctly. All right, so this process will be repeated until the mode control inputs is changed. So right now, the mode control input has been changed to 0, 0. So in 0, 0, the whole mode is activated, where it will retains its previous output. Okay, so the parallel output will retains its previous output, so it will retains the value of 1, 0, 1, 1. Okay, and as you see at the end of this the timing diagram, the clear mode is activated again. Okay, at this state, so the output will become 0 because it is in reset mode, as the shift registers has been reset. Okay, so what can I say in order for you to answer the question for 74X194 IC? First, you need to observe the mode control inputs. Okay, so you need to identify what is the current mode which has been activated inside this bidirectional IC. And then for each mode, you need to identify what happened when this mode is activated. For example, when the load mode is activated, it will take whatever value at the parallel data inputs. At shift right mode, it will take the data from SR/SER will be transferred in each clock pulse. In shift left mode, the data that comes from SL/SER will be transferred at each clock cycle. And in hold mode, whatever the previous output data will be retained. Okay, so you need to identify what happened in each mode and how to identify the mode control inputs. So that is the most important things that you need to know in order for you to operate the 74X194 universal bidirectional IC. Alright, so next we will go to the next subchapter, which is the shift register counters. So what is actually shift register counters? So first I will go through the introduction of shift register counters. So shift register counter is a shift register, of course, with serial output connected back to serial input to produce special sequences. Okay, so for shift register, there are two types. So the first type is ring counter. The second type is Johnson counter. Okay, so in this chapter, you will learn both types of shift register counters. So in general, actually, shift registers counter is similar to shift register, but the only difference is that the output will be connected back to the input because we wanted to produce some sequences. Alright? Now, we go through the first shift register counter, which is ring counter. So what is actually ring counter? So ring counter is a CISO type shift register with the final output is going to feed back to the first input. So as you can see here, this is the logic circuit of ring counter. So from this circuit, what you can see here is that you can see the final output is being fed back to the first input. So in ring counter, it has a total of 3 different inputs, which is PRE bar, CLR bar, and also the input clock. Okay. So in order to operate the ring counter, at first, the first flip-flop, which is flip-flop 0, is preset to 1 by making the input of PRE bar is equals to 0 momentarily. And all of other flip-flops are cleared by making the CLR bar equals to 0. So first, in order to initialize the ring counter, the input of PRE bar and also the CLR bar is going to be 0. So and then if we are giving the input of 0 to PRE bar and CLR bar, so the input 0 of PRE bar will make the output of Q0 to become 1, and the input 0 of CLR bar to another flip-flops will make the other output of flip-flops to become 0, okay, because it is being reset. So for the flip-flop 1, for the first flip-flop, it is being set, okay. So then the value of 1 is shifted to round the ring in the next cycle with Q1 equals to 1, while other flip-flop outputs are 0, thus represent as state 1. So at each clock cycle, the value of 1 here will be transferred to each flip-flop. Okay, so you see here, right now, the flip-flop 1 has the input of 1, so the output will become 1 later on. And then the output of the last flip-flop will going to be as an input of the flip-flop 0. So the output will become 0. So the value of 1 will going to be shifted to the next flip-flop. Okay? So it will be shifted again and shifted again. So it will be shifted all around the flip-flop. So in this ring counter, only one output of flip-flop is going to be 1, and the other will become 0. Okay? So basically, the ring counter is like the travel of value of 1 inside the each flip-flop. Okay? So for n-bit ring counter, the number of state it has is n, mode n. So for this is example of 10-bit ring counter. So the number of total states that it has is 10. Okay, so we call it mode 10 shift register counter. Okay, so next is the example. So for 4-bit ring counter, there are 4 flip-flops, which make it mode 4 counter. So for ring counter, if you are given the number of bits, for example 4-bit ring counter, it means that you have a total of 4 different flip-flops. Okay, so for 4 different flip-flops, we call it mode 4 ring counter because it is 4-bit. So in ring counter, only one flip-flop output is high. Okay, as I mentioned before, only one output of flip-flop is high while others are low. Thus, every state has unique 1 based on the position of 1. So you see here, this is the timing diagram for ring counter. So at this is as you can see here, it has a total of 1, 2, 3, and 4. It has 4 outputs, so it means that it has 4 different flip-flops. Therefore, it is 4-bit ring counter. Okay. Okay, for 4-bit ring counter, at each clock cycle, the value of 1 will be transferred to each flip-flop. Okay, but the condition is that only one flip-flop has an output of 1. Okay, you see here, at the first flip-flop, Q3 has the output of 1. At the at the first flip-flop, only Q2 has the high state, the output of 1. At the second flip-flop, Q1 will become high and the others will become low. And at the third flip-flop, Q0 will become high and the others are becoming low. And then in the next clock cycle, the process will be repeated again. Okay, where the Q3 will become high and it will rotate again. Okay, so the process will be repeated and repeated. Okay, so this is the truth table for 4 bits ring counter. Okay, so you can see here the value of 1 is being transferred at each clock cycle. Okay, this is the clock pulse which represent the clock cycle, and the process will be repeated back in the next clock cycle. Okay, so for a total of 4 bits of a ring counter, it needs a total of 4 different clock pulse. Clock pulse 0 until clock pulse 3. So it has a total of 4 clock pulse. Okay, in order for the value of 1 to be rotating for to each what we call flip-flops inside the ring counter. Alright. So next is the Johnson counter. So what is the difference between Johnson counter and ring counter? So Johnson counter is also known as Mobius counter or twisted ring counter. Okay, so this is the logic circuit of Johnson counter. So previously I've already shown you the logic circuit for the ring counter, where the output of the last flip-flop is going to give a feedback to the first input. So the Johnson counter also acts as the same, but the selection of the last, what we call the last output of flip-flop is going to be changed, where the ring counter choosing the Q3, but the Johnson counter choose the Q3 bar as the output, which is going to become the feedback to the first flip-flop. Okay, so it choose Q3 bar to give as a input in the first flip-flop. So in Johnson counter, the last complemented output is fed back as an input to the flip-flop. So the number of unique state are 2 times the number of bits. Okay, so from what you call in the ring counter, the number of unique state are the same as the number of bits. Where, for example, if we have 4 bits of 4 bits of counter, the number of unique state are 4. But for Johnson counter, the number of unique state are 2 times the number of bits. Okay, so for example, this logic circuit shows the 4 bits of Johnson counter. So it has a total of 8 states, because 2 multiplied by 4 equals to 8. And if we have 5 bits Johnson counter, we will have a total of 10 states. Okay, so that are the differences between Johnson counter and ring counter. Okay, so example, so for 3-bit Johnson counter, there are 3 flip-flops which make it mode 6 counter. So the Q2 is connected to D0. So this is the example of the 3-bit Johnson counter as I've been showing you in the previous slide. Okay, so for Johnson counter, it only has one input, which is the input clock. Okay, so the what you call the output of Q2 bar will be connected to the input of first flip-flop. Okay, so for Johnson counter, in order to operate the Johnson counter, first all of the input are initialized to 0. Okay, so as Q2 is equals to 0, Q2 bar will be equals to 1, and then 1 will be fed back to the first flip-flops, and then in the next clock cycle, as 1 is going to become the input of the first flip-flop, the output of the first flip-flop will become 1. Okay, and then as you can see here, the output of Q2 is still 0. So the output of Q2 bar is still 1. Okay, so 1 will be transferred to the first flip-flop again, and 1 will become the input for the second flip-flop. So in the next clock cycle, the second flip-flop will become 1, and the first flip-flop is also becoming 1. Okay, so for record, Q2 is still 0 because it hasn't received any input of 1 yet. Okay, so Q2 bar will become 1 again, and it will be rotating and transfer again. So right now, after the third clock cycle, so the output of Q0 is becoming 1, the output of Q1 is become 1, and the output of Q2 is become 1. And right now Q2 bar will become 0. So 0 will be rotating back to the input of D, so it will mix the output of the flip-flop, the first flip-flop will become 0. Okay, so the process will be repeated back. So after the 6 cycles, the pattern repeat again. Thus 6 unit states mode 6. Okay. So actually, in order for us to define the number of states, so the number of states is defined as the number of Unix combinations. Okay. So for example, in this what we call 3-bit of Johnson counter, it has a total of 6 Unix states, where after the 6 Unix state, the what we call the states will be repeated again. Okay. So first is 0, 0, 0, okay, that we can get in the initial, and then 1 will be transferred to flip-flop 0, and then 1 will be transferred to flip-flop 0 and flip-flop 1, okay, and then we can get 1, 1, 1 for all the what we call flip-flop output, and then we can get the state of 0, 1, 1, 0, 0, 1, and then it will rotating again, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, and 0, 0, 1. So for this Johnson counter, it has a total of 1, 2, 3, 4, 5, 6 unique states. Okay, for 3 bits Johnson counter. Alright. So you see here, the initial state is 0, 0, 0, and then after 1 is being transferred to Q0 via Q2 bar, okay, so it will be transferred in the next cycle, and all of the value of 1 is being transferred at the 3rd clock cycle, and then it is the sequence is continued again until the 6th cycle, okay, and then it will be repeated again. Okay, so this the what you call the clock cycle is what you call the pattern of the Johnson counter will be repeated again after a total of 1, 2, 3, 4, 5, 6. Okay, after a total of 6 sequence. So it will the what you call the pattern will be repeated again. Okay. So next is Johnson counter characteristics. So for n-bit flip-flop, the mode is to the power of n. The mode is 2 multiplied by n. So for Johnson counter, there are always exists 2 bits that are unique compared to other state. Okay, so it means that it only requires 2 input decoder to decode a state. So this is the example of the sequence number and also the flip-flop output A, B, C, and E. So in order for us to decode a state, okay, for example, the first sequence number 0, 0, 0, 0, so the unique state is A, E bar, okay, A bar, E bar, because A is equals to 0 and E is equals to 0. And then for the second state, we have the unique state of A and B. When A is equals to 1, so A, it will become A, and B is equals to 0, so it will become A, B bar. Okay, so similar to the 3rd, 4th, 5th, 6th, 7th, and 8th. So each sequence has what they call unique, okay, unique states. So for Johnson counter, there are always exit 2 bit. So only 2 bits are unique. Okay, there always exists 2 bit unique combination inside the sequence. Okay, so it means that it only requires 2 input decoder to decode a state. So table show 4-bit Johnson counter with 8 states. Okay, so each state has a unique 2 input variable. So the unique state simplify the decoder because a decoder with 2 inputs are required to decode any state. So this is the example of a decoder for state 1. Okay, so as you can see, the state 1 has the unit bit of A bar and E bar. So when the input of A bar and A bar is being fed, the output of the decoder will become 1. Okay, so actually the unique state is used to make the what they call the unique situation, where when that situation is happening, the output of decoder is becoming 1. For example, if we want our Johnson counter to become 1 at 4th sequence, so you need to give your input or you need to design your decoder which has the input of C, E bar. Okay, so the input of C has no bubble and the input of E has a bubble because C, E bar. And then you can design by using the AND gate. so that during this state, the output of your decoder will become 1. Alright? So next is the comparison of counter. So for a given n flip-flop, so the binary counter can produce the most state and the ring is the worst. Okay, so in the term of decoding, ring counter is the best because there is no need for decoder to decode each state. Binary counter is the worst because need more complex decoder. Okay, and Johnson is always in the middle when comparing those features. So this is a table of a comparison, okay, between each counter type. So the first one is the ring. So previously I already showed you that the ring counter has the same number of states, therefore it has the same number of mode with the number of flip-flops. For example, if the ring counter has a total of 4 flip-flops, so it is 4-bit ring counter and it is the mode 4. Okay, but in terms of decoder, it doesn't need the the decoder input because at each clock cycle only one output is activated, so only one output is become 1 and the other will become 0. Okay, for Johnson counter, the mode for n flip-flop, for example, if we have a total of 4 flip-flops, so the state that it has is 4 multiplied by 2, so it will become 8 states, so it will become mode 8 flip-flop, mode 8 counter. Okay, so in terms of decoder input, so in order for the Johnson counter to have the output of 1 at each clock cycle, okay, so for Johnson counter to have the output of 1 for only one output of flip-flop at each clock cycle, it needs a 2-input decoder. Okay, so that at each clock cycle it will have only one output of flip-flop is becoming 1. Okay, so next is the binary counter. So binary counter has a total of 2 to the power of n mode for n flip-flop. For example, if we have 2 flip-flops inside the counter, so it is mode 4 counter, so 2 to the power of 2 is equals to 4. Alright, so the decoder input is enormous because we usually need a more than 2 input decoder, so it is quite complicated for us to design the the binary counter for decoding functions. Okay, alright, so I think that's all for this chapter, and thank you.